7.7, reciprocal trigonometric functions. Work through the following with me. Complete a table of values in radians for one period of f of x equals cosine of x. And for your greatest benefit, you should do this. You should pause the video and do this yourself, and then check your work against what I'm going to enter. Cosine of negative pi would be negative 1. The cosine of negative 3 pi over 4, that is going to be negative root 2 over 2. The cosine of negative pi over 2 is going to be 0. And the cosine of negative pi over 4 is going to be a positive root 2 over 2. The cosine of 0 is 1. The cosine of pi over 4 is root 2 over 2. The cosine of pi over 2 is 0. The cosine of 3 pi over 4 is negative root 2 over 2. And the cosine of pi is negative 1. You could determine those values using a unit circle. You could have memorized them, but if you have not memorized them and you're utterly reliant on building a unit circle, start heading towards having those values memorized. Now, there is another function called the secant function, which we define as 1 over the cosine of x. In other words, secant is equal to 1 over cos x. Using your table for f of x equals cosine of x, what we just built above, you should plot the points on a graph for secant of x. So in other words, we're going to be plotting points that corresponded to 1 over cosine of x. So we're inverting, we're not inverting, we're taking the reciprocal of all of our values up above. And ask yourself, what does it mean to have 1 over 0 for some of your points? We'll leave that for consideration and work our way towards it. Okay. Now, when we are at 0, we said that the cosine is 1. 1 over 1 is still 1. So let's call this 1. Let's call this negative 1. Those will be an easier scale to work with. Okay. Now, let's take a look at the easy points first, right? When we were at negative pi, so we'll go out to here. Negative pi, we had a value of negative 1. So 1 over negative 1 is still negative 1, so no change there. And at pi, when x was pi, cosine of x was negative 1, so 1 over negative 1. That, again, lands right there. Okay, now let's look at some of those interior points. If we do root 2 over 2, and we flip that, that would be 2 over root 2. So at negative pi over 2, we'll have 2 over root 2. And that gives us root 2, 1.4. Oh, that's interesting. That's bigger than 1. Well, that's kind of significant. Yeah, 1.4. So right about there, because remember we're looking at negative pi over 4. And pi over 4 had the same value, so that would put me right about there. Yeah, fascinating. And than when we did negative 3 pi over 4. Negative 3 pi over 4. That was similar, but it pushes down in the other direction. So negative 1, negative 1.5. Looks like on that one, we're going to be around here. Okay, and then similarly on 3 pi over 4, it was also negative root 2 over 2, so that would put me down right about there. And now we said we had some other things going on here. We've got the negative pi over 2 problem. Negative pi over 2 is 0. And if we're looking at the secant of x, which is 1 over the cosine of x, we're going to have 1 over 0 as a value. But 1 over 0 is undefined. And this is where it does ask us the question, what does it mean to have 1 over 0 for some of your points? Well, if you remember our past life, whenever we had a rational function and we had 1 over 0, that was where we had a vertical asymptote. Vertical asymptote. Okay, so that means that if we're going to have to look at 1 over 0, we actually have a trig function that has a vertical asymptote at negative pi over 2. And the same thing is going on at positive pi over 2. This is not dissimilar from tangent in that way. Well, now let's smoothly connect our dots. And keep in mind that tangents require us to keep pushing up from those points. It also looks like we should maybe add in some more points here. We know that if we look past negative pi, if we head out to negative 5 pi over 4, that's going to give us a value down here as well. And negative 3 pi over 2 also, the cosine of negative 3 pi over 2 is also 0, so 1 over that will also be an asymptote. So if I connect smoothly, I wind up with that. And yeah, let's go ahead and, no, go away, come back. Let's go ahead and continue to symmetrically sketch in the rest of that behavior. Okay, so this is the graph of secant of x, and it repeats, it continues on. You may see a ghost of the cosine graph lingering here. We could do something to make it a little more evident. If we wanted to, and it would be completely reasonable, we could say, well, you know, here's where cosine used to go. And here is the result we get in heavy lines when we look at 1 over cosine. So we have our cosine trace, and then we have 1 over all the cosine values. Most particularly, we get those asymptotes where we would have 1 over 0. And this is the graph of the secant of x. So whenever you see a problem calling you to use the secant of x, you should look at 1 over the cosine value for the same angle. And it's trig, so you should expect this to be somewhat repetitive, similar to the relationship secant of x equals 1 over cosine of x. There's a corresponding reciprocal relationship for f of x equals sine of x. we define the cosecant function as cosecant of x is equal to 1 over sine of x. We're going to do the same thing we did above. We're going to build a table this time for sine of x, then we're going to use that table to calculate 1 over the sine values and produce a graph of the cosecant of x. So we're only looking at sine of x values right now, and we'll walk through these. Again, this is an opportunity for you to do it yourself. You might want to take a moment. Sine of negative pi is 0. The sine of negative 3 pi over 4 is negative root 2 over 2. The sine of negative pi over 2 is negative 1. The sine of negative pi over 4 is also negative root 2 over 2. The sine of 0 is 0. The sine of pi over 4 is positive root 2 over 2. The sine of pi is 1. 3 pi over 4, we've got, again, positive root 2 over 2. And the sine of pi is 0. Okay, so we might start our work this time by sketching the asymptotes. We know if we are graphing cosecant of x, that is 1 over sine of x. If we're plotting those points, we're going to wind up with asymptotes anywhere we had a 0. So these are going to be the asymptotes for cosecant of x. And let's go ahead and get these asymptotes onto the screen. We'll represent them as dotted lines. So we have them at negative pi. We have one at 0. We have one at pi. And we could project that we would also have asymptotes at negative 2 pi and asymptotes at 2 pi. Okay. Now, as before, we have some values that are very easy to work with. If we are doing 1 over, remember 1 over the sine value, so looking at the reciprocal, 1 over 1 is still 1. 1 over negative 1 is still negative 1. So these are the ones that we'll get on the board early. So pi over 2, sine is 1, so then cosecant is 1 over 1, still 1. Negative pi over 2. That negative 1 is unaffected. And that this does predicate that I'm labeling this as 1 and this increment as negative 1. So there we go. Now let's look at what happens with some of our other values. If we are looking at pi over 4, say we're doing root 2 over 2, when we do 1 over root 2 over 2, that gives us at pi over 4 again the value 1.4. And on the negative side, we see similar behavior. If we go out to negative 3 pi over 4, we get negative root 2 over 2 again. Similarly over here, if we go out to positive 3 pi over 4, we get positive root 2, or positive root 2, yeah. And we could again connect smoothly and complete our swoops. Because these are trig functions, we can expect them to be repeated in a symmetric fashion. So yeah, we're going to have another set of 3 points down here. Let's tidy those up a little bit because we do know that it's 1.4, so it's closer to the negative 1.5 than I was doing it. Go like that. Okay. And let's push over on the left at negative 3 pi over 2. Back up to 1. And there we go. we can again sort of sketch the ghost of the graph of the sine of x. It's lingering inside of here. If we think about it having the following behavior. So there in dotted lines is our graph of the sine of x. And we have these curves, the solid curves, which are 1 over the sine of x. That is the cosecant function, cosecant of x. Tangentially related. Well, of course, if we have reciprocal functions for sine of x and cos of x, we must have one for the tangent of x too. And we define the cotangent function as cotangent of x equals 1 over the tangent of x. So, time to build a table of tangent values. So the tangent of negative pi. Well, that is the tangent value of negative pi is y over x, so that's 0. The tangent of negative 3 pi over 4 is negative 1. The tangent of negative pi over 2 is undefined. The tangent of negative pi over 4, that is, again, negative 1. The tangent of 0 is 0. The tangent of pi over 4 is 1. The tangent of pi over 2 is undefined. And the tangent of 3 pi over 4 is 1, with the tangent of pi being 0. And I have made a mistake here. The tangent of 3 pi over 4 is not 1. It is negative 1. And let me double check myself. I do have another mistake. The tangent of negative 3 pi over 4 is not negative 1. No. It is positive 1. Okay. So having clarified my own mistakes, we're good to graph this. But we're not going to graph this. Remember, what are we going to graph? Using your table for tangent of x, plot points on a graph for cotangent of x. Okay, so cotangent of x, this would be 1 over the tangent values. But this presents an interesting conundrum. And it may be useful at this point to note that where tangent was undefined, it's because it had the value 1 over 0. Okay, we'll come back to those. If we're going to do 1 over tangent, it is clear that we will have asymptotes wherever tangent itself was 0. So these are going to be the asymptotes of cotangent of x. So at negative pi, we'll drop on through. At 0, we'll put an asymptote. Also at pi. Okay, and things repeating as we expect them to, we should also have asymptotes at negative 2 pi and 2 pi, even though they're not on our graph. Let's add other points. Okay, remember, we're doing 1 over the value of tangent. So negative 3 pi over 4. Negative 3 pi over 4 shows up here. And we are saying that it is 1. So 1 over 1 is still 1. That's convenient. I'm going to let that be 1. Let this be negative 1 again. Now, this is the interesting bit. If for tangent at negative pi over 2, we were 1 over 0. For cotangent, we are now 0 over 1. 0 over 1. Yeah. which is just 0. So there we go. And negative pi over 4, that's 1 over negative 1, that's still negative 1. Yay. So there's our first period. There's our first period of cotangent. We connect our dots smoothly. And there's a graph. Yay. Okay, now, just as the cotangent of pi over 2, or negative pi over 2 was 0 over 1, the cotangent of positive pi over 2 cotangent of positive pi over 2, it will also give us 0 over 1, which will give us 0. So there we go, cotangent of pi over 2. And we get the similar behavior. Pi over 4 goes to 1, negative pi over 4 goes to negative 1. There's our nice clean swoop. Okay, so, and we can keep repeating this. We don't have to keep calculating values. We can just replicate the pattern and say, yes, indeedy, there is my graph of the cotangent of x. Now, there's a special relationship between the cotangent of theta, the sine of theta, and the cosine of theta that can be shown in a couple steps. This is rather like proving those angle identities that we looked at in problems 16, 17, and 18. I want you to use algebra and the definition of cotangent to show that the cotangent of theta is equal to cosine of theta over sine of theta. And if you feel that you could do this on your own, give it a shot before you see me do it. Okay, well, let's start with our very raw definition of cotangent. So we will say we know that the cotangent of theta is equal to, right back where we originally defined it, 1 over tangent of x. And this would be equal to, because tangent is sine over cosine, so this would be equal to 1 over sine of x over cosine of x. Oh, but I'm using x and I should be using theta. Poor form. There's the thetas. Okay. Well, anytime you're dividing by a fraction, you should invert and multiply. So this would be equal to 1 times cosine theta over sine theta. Oh, what do you know? There we go. Cosine theta over sine theta. Cotangent of theta is equal to cosine theta over sine theta.